Hello everyone, my name is Mingwei Zheng. I'm glad to introduce our recent work, RFCAudit, AI agent for auditing protocol implementations against RFC specifications. Network protocol reliability is critical. Even a single bug in a protocol implementation can lead to serious consequences, from service disruptions to security breaches and even data loss. Achieving true reliability requires two dimensions of correctness. First, low-level safety, which has been well explored through fuzzing and traditional static analysis. And second, high-level semantic conformance, ensuring the implementation truly follows the intended behavior described in protocol standards. The latter aspect, semantic correctness, remains underexplored. So, in this work, we focus on functional bug detection, identifying violations of protocol semantics that threaten the correctness and security of network systems. Functional bug detection is pretty challenging. Why? Here's an example from RFC'25, which specifies a bubble routing protocol. It says, if a bubble node loses all feasible routes to a destination but still has unexpired unfeasible routes, it must send a sequence number request to attempt a route recovery. The challenge is that the intended behaviors of protocols are defined in RFCs, which are written in natural language. These documents describe complex semantics across long informal text, making it extremely difficult to translate the specification into precise, machine-understandable logic. Let's look at a real bug our tool found in FR Auditing's bubble implementation. The original code only checks for unexpelled feasible routes, completely ignoring unfeasible ones. As a result, when all feasible routes are gone, the router never sends the required sequence number request, violating the RFC's intended behavior. An unfeasible route is one that's temporarily unusable but may become valid again. Without sending this request, the router can get stuck without valid routes, causing performance issues. Automatically detecting such bugs is extremely challenging because there's no direct mapping between the RFC text and the source code. Existing testing approaches can hardly find this bug. This functional bug violates the RFC's requirements, but since it does not crash the system, fuzzing cannot detect it. Differential analysis could help, but it needs multiple independent implementations of the same protocol, which is often not available. Even when they exist, both implementations might share the same misunderstanding of the RFC specification, so the bug stays hidden. Formal verification, while accurate, requires precisely formalized properties, which demand significant manual effort and expertise. Ultimately, all these approaches suffer from one root limitation: the lack of automated oracles for semantic correctness. So, how can we address this gap? Our key idea is to use large language models as a new kind of semantic oracle. LLMs can directly compare individual semantic properties from the RFC with localized code in the implementation. For example, we can ask a large model a simple question: find any functional inconsistency between this RFC rule and this piece of code. The model correctly identifies the issue. The code misses the unfeasible route check required by the RFC. This shows that large language models can act as semantic oracles, bridging the gap between natural language specifications and source code logic, something traditional methods cannot easily do. And beyond comparison, large language models are also very good at extracting individual properties from the RFC documents themselves. So the core problem is, how can we find the relevant code for each property within a large protocol implementation? Our solution combines code semantic indexing with demand-driven retrieval. We begin by building a bottom-up hierarchical semantic index of the entire code base, starting from individual functions to summarizations, then aggregating these summarizations into file-level summarizations, and then finally directory-level summarizations. On the left is a raw repository structure. Under the bubble directory, files like route.c and message.c contain multiple functions. On the right, we show the hierarchical semantic index, which preserves the original file system structure but is enriched with large language model-generated summaries. For example, route loss handles route recovery, while send update resend transmits routing updates. This semantic map makes it much easier to localize the code segments relevant to specific RFC properties. Once we have the semantic index, the next step is demand-driven retrieval. That is, retrieving only the code that's relevant to a given RFC property. Let's walk through how that works with our run example. Using the hierarchical index, the system identifies that the function route loss is most relevant, so a retrieval agent retrieves the definition of the route loss function. To verify the RFC behavior, the agent requests more context on demand, retrieving correlate functions like find best route to examine how route recovery is implemented. Finally, after analyzing both the property and the localized code, the system detects the inconsistency. Here's an overview of the RFC audit workflow. It consists of two main phases. In phase 1, the indexing agent builds a hierarchical semantic index of the entire codebase. In phase 2, the detection agent takes semantic properties extracted from the RFC and iteratively retrieves, examines, and validates code segments against the RFC properties to identify inconsistencies. Using this workflow, RFCAudit uncovered 47 functional bugs across 6 real-world protocol implementations, with an overall precision of 81.9%. You can find more technical details and evaluation results in our paper and code. Thank you.